In this section of alkane, we're going to talk about cyclic or ring compounds, and they're called cycloalkanes. On the left-hand side, you see cyclopropane. That means if I have 3 carbon, we call it propane, but when these two ends come together and you make a bond, then you get cyclopropane. From geometry, we know that whenever you have triangular shape, each angle is going to be 60 degrees. But keep in mind, hybridization for each carbon would be sp3. Why? Because you have 2 hydrogens here. Let's just look at one of these carbons. 2 hydrogens and 2 bonds. That's 4 pairs. And that's sp3. And with sp3 hybridization, you would expect 109.5 degrees. However, the angle here is 60 degrees. That means in order to make a cyclopropane from propane, you have to squeeze the angle from 109.5, which is expected, to 60 degrees. So in other words, there is a bond strain in here. That means you are forcing this angles from expected 109.5 degree to 60 degree. And that's why these molecules are not that stable, and in organic reaction they would break down quite easily. Similarly, if you look at cyclobutane, again here it made a four-membered ring compound, and each angle is like 90 degree. Again, it's shorter than expected 109.5 degree for sp3 hybridized carbon, because each carbon at the corner would have sp3 hybridization. Now, naming of cycloalkanes. First, you need to count the number of carbon atoms in naming and use prefix cyclo. For example, if you look at the example on the left-hand side, first I'm going to count number of carbon in this ring compound. Each corner has a carbon. So 1, 2, 3, 4, 5, 6. With 6 carbon, normally you'd call it hexane if it doesn't form a ring, but in this case it formed a ring, so we'll call that cyclohexane. Now whenever you have substituent groups attached, substituent groups means anything other than hydrogen directly bonded, because hydrogen is not considered to be a substituent group. So in this case, I have this methyl group as substituent group. This methyl is another substituent group. So we need to mention where these groups are. Now here, in order to number these, you need to start at the point of attachment. So your one has to be, you start with the point of attachment of the first substituent group. So this is number 1. Now the question is, how do you have number 2? Would it be on your left side or on your right side? The rule says that it should be on the right side so that we can get the lowest sum. So if I have on the right side, 2 is on the right side, then this is going to be 3. So I have 2 substituent groups, one at location 1, one methyl group, and location 3, I have the other methyl group. So 3 plus 1 is 4. If I go the other way, let's make the other way. 1, 2, then this is going to be 3, then this is going to be 4, and this is going to be 5. So in that case, you would have one group, location 1 would have one methyl group, location 5 would have another methyl group. 1 plus 5, that makes it 6. So it's not acceptable. So in other words, your numbering has to be from 1, 2 to 3. From this carbon, which I wrote down as 1, to the right carbon, to the next right. So that's how this would give the smallest sum. So that's why this compound is 1,3-dimethyl cyclohexane, not 1,5. Now come to the next example. Again, I'm going to first count number of carbon atoms in the cyclic structure. So this is going to be 1, 2, 3, 4, 5. 5-membered carbon is pentane, but since it made a cyclic compound, so it'd be cyclopentane. So this is cyclopentane. That'll be the end part. Now there are two substitution groups. Let's highlight them. One is the methyl, the other one is 2-carbon substitution group is ethyl. So how do I number these? Again, you must maintain the smallest sum. Not only that, you must have alphabetic priority. Methyl starts with M. Ethyl starts with E. So in numbering them, where would I assign one? This one, where ethyl is attached. So my number 2 has to be this. So 1-ethyl, 2-methyl cyclopentane is the name of this cyclic compound. Let's do one homework problem, and this is coming from your textbook, which is Fundamentals of Organic Chemistry, John McMurray, 7th edition. Now I'm going to draw a structure for 1 tertiary butyl 2-methyl cyclopentane. Always it's a good idea to start with the end part. So cyclopentane, so I say cyclic structure 1, 2, 3, 4, 5. So this is cyclopentane. So I'm done with this end part. Then I must have 2-methyl and 1-T-butyl. It doesn't matter which one it gets 1. Any corner can get 1. So this corner, let's call it 1. So let's first assign 1 and then 2. Now this will be T-butyl. Remember T-butyl? You must have carbon bonded to 3 other carbon. That's how you get tertiary. At your level, I used to remember it by imagining T. So this is like a T with carbon. So that gives you T-butyl or tertiary butyl. In the second position, you must have methyl group, and which is fairly easy. Now keep in mind, these are without the hydrogen. But if you want to stick in hydrogen, there'll be 3 hydrogens attached to each of these carbons. So you have 3 hydrogen here, 3 hydrogen here, 3 hydrogen here, 3 hydrogen here. So this is 1 T-butyl or tertiary butyl 2-methyl cyclopentane. Here we're going to discuss about isomers. Isomers have the same formula but different structures. So basically they're different compounds even though they have the same formula. So there are 2 types of isomers we are going to discuss here. It's called cis, when substituent groups are on the same side. Trans, when those substituent groups are on opposite side. Now keep something in mind. Quite often we are misled by this definition. You cannot convert cis to trans or trans to cis without breaking a bond. So if sometimes it may seem to you, like for example in bottom example, the way I have presented this, these 2 Cl are on the opposite side. On the right hand side, these 2 Cl are on the same side of the molecule. The question is, would I call this one cis, right hand side molecule cis, and left hand side trans? Answer is no. Since there is a single bond, I can simply rotate this compound so that Cl from the top, it can come to the bottom. So when you can interconvert from one to the other, that means it's not a cis-trans isomer. It's not an isomer, it's the same compound. So if you have a distinctly different compound, you should not be able to interconvert by simple rotation around a bond. So when you have a single bond, cis-trans isomer in a non-cyclic compound is not possible. But when they make a cyclic compound, then it's possible. Here, you can see here, this is a cyclopropane. This is methyl group. This is the other methyl group. These are 2 substitution groups. They're on the same side. So obviously is cis. If I had this methyl group to the bottom, like you see here, they're on opposite side of this molecule, and that's why it's trans. You cannot convert from one to the other without breaking a bond. So if you have a model, try to make it, and you see that you can't interconvert. This is something I already discussed, that cyclopropane, there is a angular strain and weaker CC bond. So it's not a highly stable compound. As you add carbon atoms, angle gets larger and approaches 109.5 degree. So we already talked about cyclobutane, which has 90 degrees. Still there is some angular strain, but beyond that, cyclopentane, cyclohexane, heptane, they have 109.5 degree. Again, by making a model, you can better understand these. Now, cyclohexane can be in two forms. One we call boat, the other one is called chair conformation. Now, this shows only the carbon and no hydrogen. So keep this in mind that each corner has a carbon. So this is carbon. So this is like a boat, and this is on the right hand side, you got a chair conformation. The chair conformation is more stable than boat conformation. If you have a molecular model, you can make something like this, which is a chair conformation. Pay attention to the fact that in chair conformation, this is the chair conformation if you just go by these carbons. Okay. Now in chair conformation, these are called axial atoms. There are three of them are axial atoms, and the three axial on the top, three axial on the bottom, and rest are we call equatorial, which is around this hypothetical circle. So these are the equatorial hydrogens. Now, the same thing is shown on the right hand side with the stick bond. We call them stick bond because these are the carbons. Now you can better see this connectivity. And this chair conformation is more stable than boat conformation, because in boat conformation these hydrogens would get much closer, and that's not a very good situation because they repel each other. In this slide, you're looking at two chair conformations. We can just flip from this one to this one. The big difference you see here, the methyl group, in this case is in axial position. Axial position is the perpendicular position to the ring structure of 6 carbon atoms. So these are approximately, it's a plane, even though we know that in exact sense it's not a plane. 6 carbon atoms are a little bit out of plane because of the fact that they all maintain 109.5 degree angle. These are perpendicular positions, and you have these methyl group pretty close to these hydrogens in axial positions. And these are equatorial positions. They're not that close to each other. If I play with this model, I can easily go from this structure to this structure. Now what's the difference between these two structures? The methyl group, which was in axial position, this is the axial position, is now, this same methyl group is in now equatorial position. And that's more stable. They're not that close to the other atoms. And I'm going to show you soon with chemical model and a video clip that how you can convert from one structure to other structure. Since these are conformations, you don't need to break any bond. Here you're seeing a chair conformation where methyl group, this is methyl group with colored hydrogen, 3 hydrogens, they are in equatorial positions. Let me explain to you. In a hexagonal ring like this, I mean, these 3 shown in red are in axial position, and in the bottom also, these 3 whites are in axial position. Axial positions are nothing but perpendicular to the plane of the ring of 6 carbon atoms. I can change this conformation, because this is one of the conformations, and which is more stable than the other conformation that I'm trying to get. And let's play with this. Without breaking a bond, you can go from one to the other. So this is another chair conformation. You can write down these chair conformations. Now, in this chair conformation, what you see here is, again, let me move it a little bit better. So now you can see that this methyl group is no longer in equatorial positions, rather this is in axial position, and it's pretty close to these other axial groups. So that makes it very unstable compared to the previous conformation. So if a question is on between those two chair conformations, obviously this one is less stable. Now let's make a boat conformation. This is a boat conformation. This is very unstable compared to either of the chair conformation. You can see a methyl group is pretty close to this red group.